So prime factorizing 150, this one I'm going to do in a factor tree. So if we look for a divisor of 150, we can use any divisor. We can use a large divisor or a small divisor. Here I'm going to use, let's use 15 and 10. So I didn't necessarily, I could choose some prime factors, but I'm going to in this case use non-prime factors because I can still in a tree break down the 15 into even smaller multiplication pieces, and I can break down the 10 into even smaller multiplication pieces. So I can then rewrite this as 2 times 3 times 5 times 5, and that's going to give us back our original 150. The nice thing about prime factorizing is that when we look at the prime factors, we can group together any prime factors to get a factor. So we can use the prime factor as a factor. We can use group the 2 times 3 or 6 becomes a factor of 150. And we can see a lot of the divisibility properties. We can see if we group these together, 5 times 5, 25 must be a divisor of 150. So when we start combining these prime factors, we can see other divisors of 150. So looking at 244, let's do this one using our box method. So with the box method, we do want to use prime factors. So I'm going to start with kind of the smallest ones. If we can divide by 2, that's the easiest. So I'm going to divide this by 2, so I get 122. I can continue dividing by 2. So I'm going to end up with 61. Now 61, when I look at 61, we have to think, what are some divisors of 61? So this one's a little bit hard. So I can't divide by 2, I can't divide by 3, can't divide by 4, can't divide by 5, can't divide by 6. Okay, divide by 7, that doesn't work because 7 times 9 equals 63. 8's not a divisor. Once we get to that point, we know that 8 times 8 is 64, so we don't have any other divisors bigger than 8, so that's it. In fact, 61 ends up being a prime number. So we can rewrite this as 2 times 2 times 61 is equal to 244. And again, we can group these factors. We can see that 2 times 2 is a factor of 244. We can group 2 times 61, and that represents a factor also, or a factor of 244. So the nice thing again about prime factors is any combination of these primes, when we group them together, also represent factors. So 725, let's use our box method here. So we divide by 5 here. Okay, so 725 divided by 5, that's going to be, let's see here, 300. Sorry, that's going to be 145. Okay, so we divide by 5 again. We divide 145 by 5. That's going to end up being 29, and 29 is a prime number, so we leave that as 5 times 5 times 29. So 1920, we'll use a factor tree. So let's use 10 and 192. We can break down 10 into 5 times 2. Okay, so these are the ends of the factor trees. 192, this one's a little bit harder, so I'm just going to use the divisor of 2, and I'm going to end up with 96. Okay, so 96, 2 times 48. Okay, 48 is 6 times 6 times 8. So this one has a lot of factors here. So 6 can be broken up into 2 times 3, 4 times 2, 2 times 2. So this one we have to combine all the factors, so we have to make sure we count this accurately. 1, 2, 3, 4, 5, 6, 7. So it's going to be 2, and I'm going to use an exponent here, 2 to the power 7. And we also have a multiplier of 3, and we have a multiplier of 5. And that represents all the prime factors. And again, any grouping or combinations of these then must also represent divisors or factors of 100 or not 1,920. Okay, so that's the nice thing about prime factors, is they are the building blocks. They are the building blocks of numbers, and we can put them together in all sorts of combinations to get other multipliers or other factors. And we're going to use this to help us find greatest common factors and lowest common multiples later on.